Welcome back, my dear friends. A very good morning, good afternoon, good evening to all of you, wherever you are placed, whether in India or abroad. And as you know, this is the DADM 2 course, which is Data Analysis and Decision Making 2 under the NPTEL MOOC series. And this DADM 2, as was DADM 1, is basically for 12 weeks, which is 60 lectures, each lecture being from half an hour. And as you already know, I do repeat in the beginning of each class, each week we have 5 lectures, each being for half an hour, and after each week we have assignments. So, we have already completed 8 weeks, that is 8 assignments have been solved by you. And also we are in a position, we are getting queries in the forum and we are answering it accordingly. And today is basically the third lecture in the 9th week, which as you can see from the slide, this is the 43rd lecture in the 9th week. So, we are considering the concept of stochastic dominance. For stochastic dominance there was first and second. The first was the case when the CDF value for the decision A1 is greater than equal to CDF value of A2, and in the second order stochastic dominance was when the expected value of A1 was greater than expected value of A2, and I have drawn this diagram accordingly, if you remember. I will draw it again if required as we proceed. So, we will consider few of the different forms of the different way of expressions of the MAUT, which is multi attribute utility theory. I will just mention them. We would not be solving any problems apart from the very simplistic one. So, for the additive one, the utility function would be where you add up all the. So, technically, okay, let me go back a little one step backwards. So, generally you have a bundle of a decision which is bundle of criteria or attributes. Maybe for a car, I am again given the same example, a color, card, boot space, passenger space, safety, style, mileage, price, resale value, per month, maintenance cost, all these things. Some are objective, some are subjective, some can be expressed as equation, some cannot be expressed as equation, they are just characteristics, attributes. Now, for the utilities of the combination of that vector x consists of x1 to xn depending on n dimension, or it can be from x1 to xk depending on k dimension of the properties. If we can express that whole utility as the sum of the utility functions for each individually, then we have the additive function. The additive for the case if you can add up. Now, if we basically have the concept where you add up the utility function, which is good, but you also give some weightages. So, you will basically have the weighted additive function, and these lambdas based on which you find out the weights lambda 1, lambda 2, lambda 3 till lambda n or lambda 1 till lambda k, they would be known as the scaling functions for the utility functions. So, the weighted additive functions and these are the scaling functions. So, and this values of small u and this capital U are the same, they do not make any difference. I am taking a utility function as a functional form only. For the multiplicative or log additive one, you will just consider that you will basically have the combinations such that for the single units, that is u1, I am mentioning for ux1, u2 I am mentioning for ux2. For u1, u2, u3 till un, you will multiply them by the scaling factor, add them up. So, this is you are taking one at a time combination. When you are taking two at a time combination, if there are n of them, so it will be NC2. The combinations are u1 with u2, u1 with u3 till u1 with un. Then you will take u2 with u1, u2 with u2, u2 with u3, similarly the last one u2 with un, and so on and so forth. So, you will multiply them with the concepts of the scaling functions or scaling factors, which is lambda 1 for the combinations, lambda 1, lambda 2 for the combinations of I and j. So, if we have combining u3 with u10, it will be lambda 3 and lambda 10. So, we will combine them. And similarly, as you increase the combinations, you take NC3. So, you will basically have lambda I, lambda j, lambda k for the combinations of ui, uj, uk. So, here it is. So, this is I am only marking one. So, I use the red color. So, it will be easy for me to write. So, this is basically ui, this is uj, this is uk. I should be utilizing, let me use the color difference, so it will be easy for me to explain also. This is uj, uk. So, the kth one goes with the kth one, the jth one goes with the jth one, and the ith one goes with the ith one. So, you will have different combination. If you can put the higher combination, it will be given. I am using the color red only as it is able to differentiate. So, it will be NC4 combinations. So, I will write in different colors now. So, these are the combinations NC4. So, now if I write it, it will be lambda I1. I am using the suffix I1, I2. So, it will be easy for me to differentiate, not IJKL. I could have used that, but I am not going to use that. And obviously, the corresponding factor. So, I should leave space so I can write. So, it will be UI1. When I use the second color, lambda I2, UI2, then green lambda I3, UI3, so lambda I4, UI4. So, these combinations go along, this combination go along, this combination go along. Go along means the weightage scaling factors which I am giving, and this combination go along. So, I basically multiply them and have that value. So, here n is the number of utility functions, while lambdas are the scaling values which I have for each function. So, here what I am doing, I am taking NC1 combinations, NC2 combinations, NC3 combinations till the end last one, which is NCn combinations. It is basically trying to find out the joint probability distribution. First case is the marginal case, then you have the joint distribution, bivariate case, trivariate case, so on and so forth. In the decomposable form, the utility function u x1 to u x n is given by a functional form where it is now a function of the utilities taken individually. So, it is u1, u2, u3 till the last one which is taken as un. So, I have a functional form which basically gives me an output is the decomposable form of the MAUT. For the additive non-transitive decomposition, if we have the functional form where x is greater than y, in the sense that it dominates y, x is a bundle, y is a bundle of decision. Bundle means those is a vector. So, you will basically have for any combination of ui for x and uj for x, you will basically have the functional form always dominating and greater than 0. Similarly, you have the multiplicative utility function where you multiply the utilities individually, considering that u1, u2, u3, u4 until the unth one, and you have been able to break them into individual part. In the multilinear case, you will basically have a combination of some of the UKs where you multiply and then multiply those factors by a lambda j corresponding to the fact that you have been able to differentiate the whole utility function into, say for example, 3 components of I has been divided into n has been divided into 3 components, which is n1, n2, n3, such that n union of n1, n2, n3 is the universal set n, and the intersection I am considering for the time being as N1 intersection N2 or N2 intersection N3 or N1 intersection N3 are on null set. Then for N1, N2, N3 I have the multiplicative factors as pi j's depending of j which is equal to I1, j is equal to I2 and j is equal to I3. So, if I have that, then the utility function which I get is the multilinear utility function. Other utility functions which I am just mentioning is the quasi additive, bilateral, hybrid, quasi pyramid, semi cube, interdependent variable and multilinear, which I have already considered. Now, we will consider the properties for the multi attribute utility theory. So, there will be two properties, I will come to that. The pair of attributes of x and y. So, x and y are basically the bundle of decision which are vectors. So, pair of attributes x or y which are elements of capital X, then we will say that x is preferentially independent of attribute z if the all the trade offs between x and z is not affected by a given level of z. So, if I have decision z and it is not going to affect the ranking system on x and y at any stage, we will basically say they are preferentially independent based on the fact and x and y are not affected by the decision or level of z. While we will say that utilities are independent, how x will be independent of the attribute y, when the conditional preferences of the lotteries of x, bundle of decision x or bundle of decision y, where x and y are element of the overall universal set x or y, whichever you denote. So, this x and y are a subset of x and y is x, small x and small y are subset of either capital X or capital Y, whichever you denote. So, capital X and capital Y are the universal set and the elements are given by the small values and they are obviously vectors. So, when conditional preferences of the lotteries on x given y do not depend on the particular level of y. So, they would be independent in the sense that you can express them as multiplicative factors. So, two attributes are additive independent when you can basically mention. So, the properties of the utility function, so of u x1 to xn can be expressed as the sum of u1 to un. So, that will be a property of additive independence, where utility function of any two bundles x1 and x2 can be expressed as the combination of u1 and u2, and it can go to n different combinations. So, n or k number of combinations depending on how you denote the vector. So, if dimensions are n and you are going to combine them n number of times depending on different type of realized values. So, obviously, it will be an additive independent to the factor of k. Now, we will consider background of multi-objective optimization theory, and here I am mentioning again, I am just giving you the picture, no solutions would be done because that will be considered in the area of DADM 3, which is decision analysis and data analysis and decision making 3, where we will consider operation research as the main focus. So, let us consider a multi-objective optimization problem where the form of the optimization is that you have k number of functions, and each is based on the fact that for some of the x's you basically take the functional form from f1 to fk. So, consider I have the decision to find out the total cost, total distance moved, and consider the total, say for example, number of cars lorries used. So, what is the background of the problem? Background of the problem, I am transporting goods from any one of the cities consider that they are, say for example, Calcutta, Patna, Bhubaneswar, Delhi, Kanpur, Lucknow, Chennai, Bengaluru, Mumbai and all these things. I am basically transferring goods from each location to the other. So, there are some distributors, they are basically transferring goods to the retailers. So, and I am the main decision maker, I am the owner of the company. So, what is my main task is to find out what is the minimum number of lorries which I utilize to transport goods, what are the goods. Consider there I am trying to transport some cars, say for example, or parts of the cars, or it can be, say for example, I am trying to transport different type of motors being of different ratings. Now, when I do that, I need to find out what is the minimum number of lorries used, because I want to have to hire. So, if the hiring cost is there, I want to minimize that, point 1. Point number 2 is that if I am going to transfer goods from any one of the cities which I mentioned to the other, from retailers point, from the distributor to the retailers, or from the main storehouses of the factory to the other retailer point, then basically I have to utilize the lorries in such a way that I am able to visit maximum of the hubs with the least number of lorries. Hubs means the places where I want to deliver, and I want to basically travel in such a way that the minimum amount of sum of the distance travelled by all the lorries taken together is minimum. That is point number 2. And consider the total cost is also minimum. Total cost would may depend on, say for example, the roads which I follow, the toll tax, the charges per hour, kilometers travelled, and all these things. So, these are costs which I want to minimize. On the other hand, maximization can be what is the total profit, what is the total sales, revenues. There can be many things. So, consider for some decisions where consider the decisions are to manufacture some quantum of the motors. The ratings are, say for example, there are 50 horsepower, 100 horsepower, 150 horsepower. So, X is a bundle of decision where x1, x2, x3 are the corresponding numbers which I produce for 50, 100 and 150 horsepower motors. So, for different values of x, these functional forms of f1 to ftk are the total cost of travel, total number of lorries which I use, total distance travelled, it can be total revenues I generate, and so on and so forth. So, when I want to optimize the combination of them in such a way that for the cost I want to minimize them, for the revenues or the profits I want to maximize them. So, the optimization word I am using is in a very general sense. Here n x which I mentioned, x1, x2, x3, which is 50, 100 and 150 HP motors, they are basically belong to the real line or in the n dimension n, where n is basically the dimension. If there are 10 products, obviously there will be 10 such items. The individual objective functions are given as f1 to fk. I am not mentioning f1x till fkx, because as you put the take out the values of x, you get the functional form of f1 to fk in the numeric value. And what you do is that for some bundle of x's which I have, I get the functional form of fi, I is equal to 1 to k into the real line, I get one value in rupees or dollars or yens, whatever it is. So, there may be many instances when the objective function are at least partially in conflict to each other, because if you increase the cost, obviously it will mean the increase the it will also have an effect on the revenues. Or let me put it the other way, if I want to increase the revenues, I have to transport more goods, more lorries would be utilized, travel has to be more. So, obviously revenues will also incur a higher cost. So, that is why we do not have any decision vector x which will optimize in the best possible manner the objective function in all the respect. That means, it is able to maximize the positive values and as well as minimize the negative values all at the same time, but I will try to find out the best optimum solution. So, we are interested to solve the optimization problem in order to find out sum of area or sum of the values of x, such that we have a multi criteria, multi objective problem based on the fact I want to maximize or minimize or optimize some of the objective function based on an outcome which is x. So, some x's are given which are elements of capital X, and I want to choose some of them x such that I am able to optimize. Now, the fact of the optimization is that they are to be optimized individually, but collectively the overall fact would be that the best solutions which I will have may not be same in the quantum front on the vector sense. That means, if I have two bundle of outputs, that means I have x star 1 and x star 2, and the individual values of x star 1 and x star 2 may not be equal. So, what I will try to show is this. So, I have, let me mention it in the. So, I have x is an element of capital X and this x is in the real line. And now the functional forms are, okay, let me mention the change the color so it is easy. So, all negative costs are red. Consider F1, F3, F4 and the positive are F2, that is why it is green, it is F5, F6, F7. Now, what we will do is that if I find out, say for example, some I, so what you will have is that there would be a positive sense, positive values would accrue from F2, F5, F6 and F7. Negative values would accrue from, so I am trying to draw it F1, F3 and F4. So, increasing one would also have a decreasing effect on the other. If it is true, then obviously we will try to increase the green one and automatically decrease the red one, green and red being the positive and negative one, but it is not that. Increasing one also would have an increasing effect on the other and vice versa, because as I said, increasing the revenue would also mean increasing the cost, because you have to sell more of the products, you have to basically utilize the transportation more and so on and so forth. Now, what I want to do is that consider there are some x's and consider these x's are, there are x, let me mention them as x1 star, this let me this is x, say for example 2 star, this x1 and 2 have nothing to do with the values of we are emptying, and consider x3 star. So, they give me the best solution. So, what is best? It may be possible that the bundle of output which I have, so they may be equal. So, what is that I am mentioning? Consider this is x1 star, x2 star, x3 star. When I have these values which I have F2, F5, F6, F7, F2, F5, F6, F7, F2, F5, F6, F7, and the negative values which I have, I am drawing the using F1, F3, F4, F1, F3, F4, F1, F3, F4. The combinations of the output which I get, the bundle net worth, if they are equal, but the individual fact of F1, F2, F3, F4, F5 and F6 and F7, individually they may not be equal. That means, the total benefit which I get for F7 either for x1 star or x2 star or x3 star are definitely different, but collectively if all of them are same, I will say that I am using the very simple concept, the net worth if I get the same, but then increase or decrease on individual front, then I will say that they are Pareto optimal such that I am equally disposed by taking the decision x1 star or x2 star or x3 star, because individually I get the net worth. I am combined I get the net worth, individually may be different, that is a different question. So, now here is the diagram and it is only possible for me to draw in the 2-dimensional case. I will try to draw it in the 3-dimensional case. Let me see how I am able to do that. So, consider the objectives we mentioned. One is along the x axis, objective 2, and along objective 1 is along the y axis. And if you see, there are in this overall space of optimization, there are 4 colors I have utilized. So, colors if you can see, AB is red in color, CD is green in color. Please note it down. it will be for your own good, you will understand. So, if you draw the diagram and if you are seeing this diagram, again I am mentioning mark AB as red, then the area or the line CD as green, because the color scheme will have important fact, while the line EF is blue and the line GH is violet. So, again I am mentioning AB is red, CD is green, EF is blue and GH is violet, while the other portions of the line for this whole area BC is black. So, it would not have any meaning, because it would not be possible for us to differentiate. So, black color I am using for the fact that I am not going to draw any conclusions from here. BC is black, again I am mentioning, DE is black, FG is black and HA is black. So, if you have drawn this, now we will proceed, based on which I will mention the concept. So, let us pay more attention on the colored line, which is AB red, CD green, EF blue and GH as violet. So, in this hypothetical example which you have drawn in a 2 dimension, it can be extended to the 3 dimensional also, as I mentioned. There are 2 objectives. It will illustrate the Pareto optimality plots for 4 different combinations of the objective functions, where the objective functions are OB, O1 and O2, which is objective function 1 and objective function 2. The bounded areas depict the hypothetical feasible set, and the boundary is considered to be the optimal set of feasible points, depending on whether it is a maximization or a minimization problem, based on the fact that you are considering the objective function 1 or 2. So, the color schemes would now become important. Point 1, the red line which you considered, which was, for the first time I will switch between this graph. So, let me make it just next to each other. So, this is the grind. So, here it is the red one. So, AB if I consider is for the case when we consider minimization objective 1 along with the minimization objective 2. Let us see. So, I am trying to minimize both of them. So, considering this, I would have this area. If I similarly consider the green, light blue or the blue and the violet one, these are the instances which are like this: maximization of objective 1 with minimization of objective 2, which is for the green one. For the light blue one, it is maximization of objective 1 and maximization of objective 2, and finally, violet one will be minimization of objective 1 and maximization of objective 2. So, violet one or minimization of objective 1 and maximization of objective 2. So, for the light blue, it is maximization of both. From green one, it is basically minimization of objective 2 and maximization of objective 1, while the red one is minimization of both. So, in the 3 dimension how it looks, I will consider that in the subsequent 2 class. So, this would be more of understanding the concept of multi objective problem, and in the last 2 class for the 9th week I will try to wrap it up with some interesting examples as required to make the things much easier for you to understand from the very simplistic point of view. Obviously, we will solve such problems in TADM 3, which I had already mentioned. With this, I will end this class and have a nice day. Thank you very much.